Thank you for coming, folks. I know it's the last session and I know you must be tired, and I think you've probably earned a little light relief. It was about 5 years ago, actually it was almost 5 years ago to the day, when Google made an announcement to the world, which you may remember. Who remembers this? They had announced that they had achieved quantum supremacy. Now, the popular press was alive with this, everybody was reporting this, but so was the scientific press. Everybody was talking about this because everybody had the same question. More specifically, what on earth is a quantum computer anyway? Because at that point it had just burst into people's imaginations. What exactly did Google do, and should I be interested in it? Why should I be interested in it? Well, spoiler, yes, you should. And the reason that you should is because actually this is real. I'm going to show you that this is not science fiction. This machinery is really being built and is really doing useful work. And somebody has to program them. Who other than us? So what I would like to do today is to, in a very short talk, of course, because I can't go into the detail, but I'd like to answer these questions. What did they do? And what exactly is the machine that they used? Now, you've heard about quantum computers, you've heard about how they're going to crack all of the encryption that we've got, and that's only kind of true. But they are able to solve the kinds of problems that we can't solve now, and actually we don't even have good language for talking about. What Google did was they solved in 200 seconds a problem that would normally take 20,000 years. Let me check that. Now, IBM, who is also active in this space, said, no. It doesn't take 20,000 years. We could have solved it in 4, but they'd still made the point, right? That they solved it in 200 seconds. And what they did was they proved the randomness, the true randomness of a sequence. They showed that this sequence could not be produced by any deterministic algorithm. Okay, so what exactly is a quantum computer? Well, in order to answer that question, we've got to understand the motivation. And our story starts, way back when. We are trying to solve problems now that are touching the limits of what we can solve. And actually, we want to go beyond the limits of what quantum computers can solve. There are big problems. And the reason that they're big and the reason that they're complex is something in the nature of the problems themselves. It's not that we need bigger computers. Bigger computers won't solve these problems. But the approach that we have to computation doesn't solve them very well. These are things like factorization now. The reason we use factorization for cryptography is because it's a very hard problem to solve. I'll show you some other examples of these problems. There are vague problems. There are problems in a factorization problem. We know it's discrete, but there are lots of problems that we want to solve which are not even discrete, that we can't even enumerate all of the cases, no matter how much time we have. And these are very useful problems to want to solve. So let's talk about this. I'm pretty sure that this is going to be news to none of you, but the simplest classes of problems that you can get are order n problems. These are trivial problems. These are the kinds of problems that can be solved by finite state machines with no memory. Now, there's a whole theory about these, and they turn out to be quite useful things, but they're obviously limited. The next scale up from this is polynomial problems. These are problems that we can solve efficiently. So they might get bigger, that you might spend more time, the bigger the problem becomes, but they do so in a sensible, controlled manner. But above this, there are a class of problems which are non-polynomial. As you increase the size of the solution expands quite a lot. But the NP non-polynomial means that having got the solution, you can test it efficiently. So you've got very hard solutions, but you've actually got relatively easy verifications. The next scale up from that are problems which are NP complete. This is things like the traveling salesman. It's hard to find the answer, but having been given an answer, it's really hard to verify it. The only way you can verify it is by solving it all over again. But all of these are based on the assumption that we can enumerate the cases. We can find every route through the cities, for example. But there is this very, very large class of problems which in normal computational theory we don't even have a name for, where the spaces are continuous, where It's about the shapes of proteins, and you can't count the shapes that proteins take up. Now, it would seem, we're not sure yet, but it would seem that the kind of problems that quantum computers can solve is some of those. Not all of them, but some of them. Here is an example of this. What we're looking at here is ferric sulfate. Now, ferric sulfate is an important, it's a salt, and it's part of biochemistry. And what we're seeing here is the chemical pathways of this salt as it goes through living systems. Now, we very much want to be able to simulate this. We want to be able to build models that are predictable. And our problem right now is that we can model this to within an order of magnitude, and that's all. If we had a quantum computer that could work at this scale, it could model all of it with very high reliability. Now, this kind of problem is what motivated quantum computers to start in the first place. It began with a conference back in 1982. Scientists, all kinds of scientists, were trying to model quantum systems. They were trying to model atoms and the interactions inside atoms. And they were finding that they just didn't have the techniques to be able to do it. So, in the course of this conference, Richard Feynman, whom you've heard of, who knew quite a lot about what these systems were, he said, well, you're trying to model it with the wrong machine. What you need, you don't want a classical computer, you want a quantum computer. And it's the first time anybody had ever said the words, and nobody had any idea what that even meant. But he just sort of breathed in and said, you want one of these, and then breathed out again, as he did. But people started thinking about what this could mean. And so in 1985, David Deutsch, who is one of the pillars of this field, he said, well, if we can even understand what quantum computation even means, that would be a start. And so he developed the idea of the universal quantum machine, sort of like a quantum Turing machine, but not exactly. But that got the ball rolling. After that, we had Shor's algorithm. Now, Shor's algorithm is the important one, the one that you've heard of. Shor has made factorization simple. If we could build a big enough computer, then it makes factorization a log n process. Not even n log n. It's very, very fast. Now, this was 1994, so there's obviously a big gap there. By 1997, Grover's happened. Now, Grover's algorithm is a search. If we take fork playing cards, Jack, Queen, King, and Ace, lay them face down, how many tries does it take? How many turns before you find the ace? On average, 2.5. In Shor's, you can do it in 1, guaranteed every time. Now, are you starting to see the power of this machinery? At this point, all of this is completely theoretical. Nobody had ever even built a machine. This was purely theoretical work. But in 2001, we built one. It was only 7 bits, but it ran, and it ran Shor's, and it ran Grover's. And at that point, the cat's out of the bag. So, what was this machine that they built? Well, in a classical computer, sorry, I'm getting ahead. This is a picture of the computer that we're going to be using today. This is, it's operated by IBM. It was built by IBM. This is quite a small one. But what you can see, down at the bottom here is a small chip which has got trapped microwaves which are doing the computation. All of this stuff around is feeding in signals to manipulate those standing microwaves. There's lots of layers of cooling. This chip has to be kept to within a fraction of absolute zero because it needs to be superconducting in order to protect these very delicate quantum states. Then this whole thing is put inside, well, it's suspended from the ceiling because you don't want anything touching it, but it has racks of machinery around it because obviously it's a complex machine and it needs to be operated, needs to be run, needs to be controlled. They put it in a flask, and then cool it down. Okay. Internally, what's it made of? I'm sorry, there's something gone really wrong with my slides. It's a quantum machine. What can I say? Okay. So here they are. They put it in the flask, and they all stand around looking really proud, because that's what you do when you're pioneering scientists. How do you use it? Well, you've seen they've got that machine. You don't have your own machine. So what you do is you build your machine, connect it to your racks of machines, of classical computers to control it, and then somebody sits and controls it. And this is very much like any other kind of online resource. In fact, what you're going to see is there are quite a lot of these machines put online as resources, just like pretty much any other resource, like those big compute grids and AI engines. But in order to understand what it's doing, we need to talk about what is special about the quantum process itself. Why is a quantum processor any different from a classical processor? And here is the answer. It's down to these quantum effects. It's down to effects that only happen in the quantum space. The first one that we have to understand is the concept of superposition and collapse. Again, some of this is going to be familiar to you, but if we have a light source and we have a screen with some holes cut in it, then what we will see on a screen over here is a series of light and dark bands. Now, this is an experiment that you perform at school, and this is the demonstration that light is made of waves. This was how they discovered, this is how they proved that light was made of waves. And most of you will have done this experiment at one point or another. But what's interesting is that if we turn the lights down so that we can count each individual photon, it turns out that light is made of these little packets. And a single photon will land only where the bright patches are. You'll see the flashes on the screen, but only where the bright bands were. And what this means is this single photon, it's a single packet of energy, but it's traveled through the screen. It's traveled through both holes at the same time, interfered with itself because it's made of waves, and finally decided where it's going to go. So what we have over here is effectively a probability distribution of how this is going to resolve. And it stays a probability field right up until the point at which you look at it. And at that point, the photon decides where you're going to see it. So what we have here, all of these probabilities, all of these different probabilities, this is called a superposition. It's a lot of states all folded down into one. And at some point, that superposition collapses and it makes up its mind. Now, is that making sense? Anybody says no? Okay, this is well established. We've known about this for years. And it seems that every single time we pass a single photon through these two holes, we're going to have a different result. The results are always going to be in the bright bands, but we're going to have a different result each time, because every time the superposition collapses, it collapses to somewhere different. Now, the next thing is the idea of entanglement. Now, I said we were generating individual photons. It turns out that if you have a light source and you're generating photons, you tend to generate them in pairs. And it's just in the nature of the physics. And these pairs are mirror images of each other, or they're twins. Each pair will have the same polarization, for example. Each pair will have the same frequency. And so what we're doing is we're drawing these photons, each with its own polarization, coming along from this light source. Now, there's nothing special about this. This is just conservation of momentum. But what's interesting is, how do we detect polarization? Well, what we do is we put a screen in the way, and we see if the photon passes through or if it doesn't. And if the photon passes through, then it was oriented, the polarization is oriented the same as the screen. And if it doesn't pass through, it was oriented at right angles. Again, you know how polarization works. And we can use this to prove that every photon matches. If we get a flash from this side, we get a corresponding flash from this side. If it's dark on that side, it's dark on this side. And it just proves the conservation of momentum. But this is true even if we tilt the screens. You see, the photon that comes through the screen is either full energy, oriented with the screen, or it's not, no matter what the orientation is. Now, this means a couple of things. First of all, it means that the polarization that we started with is itself a superposition, just like the ones that you saw. And at the point at which it passes through the screen, that's the moment at which the superposition collapses. That's the moment at which the photon decides which orientation it's polarized in, whether it's polarized with the screen or against it. But look, for this to affect that, it means they have to collapse both at the same time. This is called entanglement. This is what Einstein called spooky action at a distance, and this is what he couldn't accept about quantum theory. Nevertheless, it's been demonstrated time and time again that what happens is, this is not quite what happens, but it's a way to think about it, that when this collapses, that collapse is transmitted back in time all the way to the origin, and then transmitted forward again, so this one knows which way to go. And when we build photons, or we build bosons that are in these states where one collapse affects the other, this is called a Bell state, and we're going to be building a Bell state in a minute, later on. Is this making sense? Do you even believe it? But this is what lies at the heart of quantum computation. Okay. Now, inside a quantum computer, we are leveraging this kind of property, but we're not doing it with photons. I mean, there are machines that do it with photons, but this is not the common way of doing it. Let's look at a classical computer first. In a classical computer, if you want to represent a zero state, then what you do is you get a collection of electrons and you put them in one physical position on one side, and that causes the switch to flip. And if you want to represent a one state, then you place it into, you put them into another position, and it flips the switch the other way. So we're moving electrons each time. Now, in a quantum computer, we don't do it like that. In a quantum computer, we take one single particle, might be one photon. What we work with is things called bosons, and bosons are things which have a property called spin. I've brought some bosons. Here's one. It's not real. You'd never see it from the back of the room if it was real. But what we're looking at is a property called spin. So if we want to represent a spin, a down state, if we want to represent a zero state, then we have this in this orientation. We have it spinning down. And if we want to represent a 1, then it's spinning up. Okay? But it's one single particle. It's one single boson. In the case of the machine we'll use today, it's trapped microwaves behaving as a boson. But all sorts of things can behave as bosons. You can have whole atoms, whole gases behaving as a single boson. But it is a single particle. Now, the superpositions are important. So if that's your zero state, down, that is your 1 state, pointing up, but there is actually an intermediate state. Now this doesn't mean, I mean, we talk about rotations, and I'm going to use the language of rotations, but this doesn't mean it's neither up nor down. This means it is either up or down, but right now it's in a superposition, and it's 50-50 which way it's going to go. Okay? So let's unpack this a little. What we have here is something called the Bloch sphere. And the Bloch sphere is a sort of a mathematical model of the states this can get into. Now, you look right at the top, it's got that 0 vector. This is the way we will notate these states. It's got that 0 vector at the top, which represents spin down. I'm sorry, I didn't make this up. At the bottom, we've got spin up, which is represented by the 1 vector. And in between, we've got a whole range of different things, a whole range of different probabilities, different superpositions. But we've also got superpositions like that. So we can do rotations and rotate it back again. And there's all sorts of things that can go on. So in fact, what we're going to be doing is rotating it into a number of different states and then resolving it. So this is what the block sphere is trying to represent. Now, the block sphere itself is not even the end of the story, because what the block sphere is a projection of something called the Lie field. This is the Lie field. Now down is pointing out to the side. Really, this is not my fault. But what happens is, we start off in, let me check what this. So we start off in a down state, and then we rotate it 180 degrees into the up state. What happens if we rotate it another 180 degrees? It goes back into a down state, but do you see it's changed color? And if we rotate it again, that's a sort of an anti-down. We rotate it again, it gives us a sort of an anti-up. And then finally, we rotate it all the way back, and we get back to where we start from. So in the Lie field, rotating 360 degrees gets you into this mirror state. You have to rotate 720 degrees to get all the way back. Let me demonstrate this with my Lie pot. If I rotate it 180 degrees, you can see the duck on the front, right? If I rotate it 180 degrees, is the camera getting this? Yeah. If I rotate it 180 degrees, you can see the back of it. I can rotate it 180 degrees the other way, and you can see the back of it. But if I rotate it 360 degrees, so you can see the front of it, you see how I'm all twisted up around it? I've got to go another 360 degrees to get back to the origin again. So that is the Lie field. And that's what's happening with our bosons. When we're doing that rotation like so, that was the twisted up version of the teapot, and that is the natural one again. Okay? What makes this even harder is that these axes, the numbers, the positions that you can have on this are all complex. So on this picture, we have 4 degrees of freedom. We've got 2 complex directions. But there's a rule, and this is one of the reasons why we call these rotations, that the sum of the squares has got to equal 1. And so actually there's only 3 degrees of freedom, because once you've got 3 of them, that's pinned the 4th one. But we will be working with these complex rotations all the time. Is this making sense yet? Okay, so how do we work with these qubits? The process of computing is to set up these bits in some configuration, do some permutations on them, and then measure them. So what happens when we measure them? Well, here we go. Here is a qubit in some state. What we're going to do is we're going to pass it through a magnetic field. So there's our magnets, and as we pass it through, we get a measurement up or down. But remember that entanglement. What's happened as we measured it is that that result has been passed, not quite, backwards in time to here. So anything that was dependent on that state before it was measured is now dependent on that new state, on that measured state, later on. And that's the power. It means that we can set up problems in this superposition. And it means we can set up an infinite number of problem definitions at the same time and solve them all in one go. So, how do we do this? We'll construct a problem definition by initializing some qubits. Usually we'll try and create it as a superposition. We then transform the problem by a series of rotations and entanglements to describe the problem that we want to solve. And then we collapse it and look at a result. Now, this is only one possible result. There are many results, and they're all going to have different probabilities. So we keep doing it. We rinse and repeat. After a few thousand iterations, we're starting to see the solutions develop. Now, there are algorithms, like Shaw's, for example, which uses this to do part of the factorization, and then it says, okay, well, we've found this a little bit of information now. Let's go back and feed that back into the problem definition and have another go. So you've got this classical control loop around the outside working on the results of those underlying, of those simpler quantum results. So far, so good? Do you want to see it working? Good, because this would be a real short talk if you didn't. This it's not the real thing, I'm afraid. I've got more sense than to use a real quantum computer in a live demonstration. But this is a simulator for that computer that you saw them assembling in the IBM labs. Now, there's several things in here that I want to show you. First of all, those lines along the top, this is called the staff. It's after music notation. Bosons get introduced at the left-hand side, whoops, in a down state, and then they pass along in time until eventually they come off the end. Now, what you can see over on the right-hand side is a little cartoon, which is the simulator's guess of what the state is going to be, of what the superposed state is going to be. But as it passes that right-hand edge, it goes through a measurement process, which is over here. And I will show you those working in just a second. So let's do some work on this. And I'm sorry, this is going... Here we go. Now, what we have here is not working. Here we go. Okay. This is called a NOT gate. And what the NOT gate does is it transforms this into that. And we can see the effect of that. First of all, if you look at the cartoon on the right, you can see the ball's now filled up. So that's saying that when it's black, it says the probability of seeing a downstate is, of seeing an upstate is 0. When it's full, the probability is 1. And we can see in these results over here that we've got the bit pattern 0001 being represented as a result of all of the runs. This is running 1,000 runs to produce this result. Okay. I'm going to be fit by the end of this, aren't I? Now, if I move this gate to over there, you can see everything changed. You can see the cartoon changed on the right. You can see the results over there on the bottom left. They also changed. So that I can't get rid of it. There we go. And so now it's all zeros again, and you can see all zeros represented as our result. Now, let's compare that with this. This is called a Hadamard gate. Now, you can see what effect this has had. This has turned that into that. And you can see from the cartoon, it's got a 50-50 probability. And you can see from down here that our results are equally distributed between all zeros and 001. So that starts that, it turns that into that, and then as we measure it, that turns into either that or that with equal probability. This is now making a bit more sense, isn't it? Now, I want to show you another gate. This is the conditional NOT. Now, what this does this is an example of computation. What the conditional not does is it says, depending on the value of the top signal, it will either change or not change the value of the bottom signal. So in this case, it hasn't changed it. The top signal is down, so it hasn't changed it. But if we introduce that not gate again, the unconditional not, they've both changed. So you understand what the conditional not does. That's easy. But what happens if we put a Hadamard in there? Now, several things have happened. First of all, Q0 is gone to 50-50, exactly as you'd expect it to. But remember what I said to you before about how the model works. It's also inverted Q1 based on the result of Q0. So you can see that they are always the same. So what's actually going on here? Well, the answer is given by the cartoons. You see how the circle has shrunk? That shrunken circle says that they are impure. So, Q0, Q1. If Q1 is like that, if Q0 is like that, Q1 is like that. If Q0 is like that, Q1 is like that. If it's in that state, then not only is Q1 in that state, but they're now geared together. They are entangled. So when Q0 gets measured, Q1 moves the same way. When Q1 gets measured like that, when Q0 gets measured like that, Q1 moves the same way. That entanglement, that is at the absolute core of pretty much all quantum algorithms. Now, this is a very, very quick demonstration of what's going on. What we're looking at here is not a real programming tool, it's a tool to help you visualize what's going on. But what we do have here is enough to give you a demonstration of an actually useful algorithm which is in use in the world today. This is the quantum teleporter. Now, again, my pointer's not working, so that's why I'm having to run around the stage. What this does is on Q1, we've got Alice over on the left, and we have Bob over on the right. And Alice is trying to send a specific quantum state to Bob. Now, we can't ever duplicate quantum state, and we can't ever destroy it. This is part of the rules of how quantum mechanics works. But what we can do is we can transmit it, and this is what the teleporter does. So you can see Q0 over on the left is setting up a state, and we have a cartoon which is telling us what that state is. We didn't talk about the phase, but you can see it's changed the phase. Now, the next thing that happens is that completely independent from that, Alice produces a Bell state, the one that we just saw. We've got those two qubits entangled with each other at 50-50 probability. And then we go through a bit of logic, including a measurement process, which produces two classical bits. And the result is something. So you can see that just here on Q2 at the bottom, just at this point. Now that is not the replicated state. That is a completely random state with some very odd phases in it. And if anybody looked at it, it would collapse. But Alice sends that to Bob. And she sends also the two classical bits. And then Bob performs a computation on it, which totally restores the original. In fact, if we have time, I can show you that moving. But Bob now has an exact copy of the states that Alice sent. Now this is the basis for completely unhackable quantum communication. This is the mechanism that the Chinese embassies are using to communicate around the world. You can transmit those states through satellites. And remember, You don't need to have these things happening in this order. You can create this bell pair ahead of time. You can create it at any point along the way. So this is a really useful algorithm which will run on the simulator and will run on the kind of machines that you can get out for free. Now, before I move off from the demonstration, is there anything that you'd like to ask me about this? Okay, fair enough. I don't blame you. Here we go. Okay, 5 years ago, we saw that Google had made that announcement. And of course, it opened the floodgates. Suddenly, everything was interesting again. And so there's been a huge amount of work going on, lots of people doing work, developing the science, the theory, and the engineering. Over the last 5 years, we have produced bigger computers. More players have moved into the marketplace. Amazon has their own quantum computer now, which they're making available. Honeywell, who would ever have thought of Honeywell being in this space? We're getting more and more bits. We're getting more and more stable bits. There's a thing called quantum volume, which is how many bits you can keep stable for a certain amount of time. And the quantum volume is increasing all the time. And we will have a look at what the effect of that is in a moment. We've got new applications, new algorithms coming out. All the time. This is just a little selection of stuff from 1 year of the kind of results that are being announced, but there's lots more going on. This is a very, very active field indeed. And just to show you how active it is, here is a graph showing you the kind of announcements. The picture that you just saw, these are these announcements over time. Now, don't worry too much about the D-Wave dots. D-Wave has a slightly different thing. They've got an annealer. It's still a quantum computer, but it doesn't have the entanglement. But they're up to something like 10,000 bits now. But right now, we are up past 100. We're up to about 150 useful stable bits. But if I draw a trend line through these, I want you to notice this is a logarithmic scale. We are getting a doubling of power about every 18 months. Does that sound familiar? Now look, if you knew in 1950 what you know now about the trajectory that computers took and about the kind of jobs they did and about how they transformed everybody's lives, if you could go back to 1950 with your knowledge, how powerful would that be? It's happening again. Here's the proof of it. That's why I think you should be taking notice. So let's talk about some of the things that are going on. There has been a load of engineering going on, making much bigger machines, making more stable machines. We're working on high temperature superconduction. At the moment, it's about 0.3 Kelvin. But actually, we're playing with some really interesting chemistries now, which might get us up to like 90 Kelvin. I mean, it's still cold, but that's like liquid helium temperatures. It's not real cryogenic temperatures. And there's no reason why we can't keep bringing the temperature up. We've got new applications coming along. We talked about the physical modeling, things like chemistry, things like weather, maybe traffic flows around a city. You could use a quantum computer, for example, to find the perfect storm of accidents and signal failures that is going to gum up a city, and you can do it, and then you can fix them. So lots of physical modeling, of course. Lots of optimization problems. Optimization today is becoming a more and more interesting problem to solve. And quantum computers can help with that because they can handle optimization problems at a scale which we don't even have ways of expressing at the moment. Financial problems. not just risk management and predictions, but I mean, most of you, those of you who are in banking will understand this incredible complexity of financial computing at some levels. There is a very active development on understanding this in quantum terms. And of course, financial needs secrecy, so quantum transmission is a very useful thing to have. And I know you thought you were going to get away without hearing the word in this talk, but actually it has real implications in artificial intelligence, because the kind of problems that we solve in AI, look at those trainings that we do. They require vast amounts of data and vast amounts of power, but a quantum computer doesn't use any power at all. Everything is zero energy. I mean, the cooling costs money, but the computation doesn't. And remember, the computation is incredibly widely parallel. So at the moment, NVIDIA is cleaning up because they've got highly parallel GPU chips. Well, this knocks them into a basket. So it has incredible implications for AI and for, not just language models, but all kinds of machine learning and all kinds of database models. Security. It is true that these computers are going to wipe out cryptography, encryption as we know it. It is well known that security services around the world are currently recording as much traffic as they can with no hope of being able to decode it or decrypt it until the computers get big enough. And then they will just open everything. So not only is there a lot of activity in learning how to crack encryption, the current encryption, there is actually a bet out that by 2048, IES 2048 will be cracked effectively. Yeah, and that's not a lot of time. But on the other hand, we also want to do ordinary encryption. There is such a thing as quantum secure classical encryption. There is currently a prize out. There's a competition going on. It's being run mostly by the NSA in the US, but it's obviously going on around the world. Last year, there were 3 shortlisted contenders, and everybody thought that an algorithm called Rainbow was going to be the one. And they tested it, and they found that it's true. This Rainbow was quantum secure. That even with the best quantum algorithms, they couldn't crack it. The downside was that they managed to crack it on classical computers in 2 weeks, so that was a no-go. But obviously, there are steps and missteps along the way. But we can also resort to provably secure quantum encryption. Quantum communication, it doesn't even need it's not even encryption in the current sense. It's that you can create a secure channel that literally nobody can tap into, because if you try and tap into it, you destroy the state. And you need to destroy the state in the correct way, by binding it with something else, like one of the other parties of the bell pair. That's the only way that you can read the message. So you can spot if somebody else has got in the way because there's nothing there to read. And they can't read it because they haven't got the other side of the communication. And I'm expecting that within 5 to 10 years, you will have a quantum security chip in your laptop, exactly the same way that you have the TPS chip in there now. Because by then, it's a small enough problem that you can solve it on a chip. It'll be small enough that you can solve it with the modest power that you get in a laptop, and we will have the chemistry to be able to do it at the kind of temperatures you can achieve in a laptop, which is up to about 150 Kelvin. You can refrigerate a chip surface down to about 150K. So, I'm excited about this. It is a huge field. There's a lot going on. It is interesting. If you try and understand what's going on in this quantum world in terms of the world you understand, it doesn't work. I mean, it doesn't make sense. But on the other hand, if you can understand it mathematically, then if you understand the maths, then you understand what's going on. And there's actually a school of thought in the philosophy of physics that says, shut up and calculate. On the other hand, of course, what's going on inside a quantum computer is a much more simple version of that. I mean, you have to understand the basics of superposition, but the grammar of what's going on in a quantum computer, you just saw, actually, it can be drawn in a picture that you can color in with your own crayons. The principles aren't hard. In the same way that a classical computer, you don't have to handle the whole complexity of electronics. They give you a simplified model of computation, which you use in order to solve compute-type problems. Well, the quantum computers do the same thing. You've just got to engage with it in its own terms. So if you want to get involved, the field is wide open. There are loads of people who currently are operating quantum computers online. I've been using the IBM machine, but Amazon has one, Microsoft has one. There are quite a lot of them out there, and they will give you free time. They'll give you simulators. They will give you free machine time. I mean, you know, IBM, they've got, I think, a 50-bit machine, which you can get 10 minutes free a month. And 10 minutes is a hell of a long time when you think of lifetimes in sub-microseconds. 10 minutes gives you an awful lot of computation. So if you want to get started, here are some books. That one in the middle, Nielsen and Chang, is the absolute classic. It's quite a big book. It takes you from the absolute basics of the quantum theory that you need to understand computation. It talks about computation. It gives you examples of algorithm. It comes at it from 6 or 7 different angles. It's a really, really good introduction. It is only an introduction. It's a bit old now, but it certainly is a good place to start, and that's on Amazon. Quantum computing, a gentle introduction. They lie. But the material's good. And quantum field theory in a nutshell, if you really want to understand the theory about how these things work, that's the book to tell you. But I warn you, it is a very large nutshell. And of course, the computer that we were using is there. Okay, that's everything I have for you. Oh, apart from that, that gives you a basic introduction as well. That's everything I have for you. I hope you've enjoyed it. I hope it's been helpful. I hope it's been entertaining.